Now let us start today. Today's lecture. Last week you got the introduction to peridynamics. Now we are going to discuss, this is the point 2, lecture number 2. It is called peridynamics versus classical continuum mechanics. So peridynamics is abbreviated by PD, and classical continuum mechanics will be abbreviated by CCM. So PD versus CCM. But first we start with one-dimensional problem for one-dimensional root. So remember, we started the classical continuum mechanics with this, okay, to follow the basic idea. Okay? If you understand them, then it will be not a big problem to generalize it for 3 dimensions. Okay. First, after some short introduction, we derive, or we write down the balance of momentum that means we recap CCM, and then we develop PD, similar stuff for PD. So 2, 3. We derive the power, mechanical power, and energy identities or energy. 2.4 constitutive equations. .5 equation of motion, and 2.6 boundary conditions. So for this all stuff I need approximately 3 lectures, and after that, because we derive the equation of motion plus boundary conditions, you may start to solve them. Okay? The solution will be analytical or numerical. So, but before doing this, I would like to derive these equations and to show you all the basic features of peridynamics. So, as a short introduction, remember the classical continuum mechanics. What is it? We used many times. So this is our reference body, clamped, and if you apply the loads, the body is going to deform, and you get the actual configuration, something like this. We discussed it many times. So sorry. If you apply the load, the solid is going to deform, and you get something like this. And this is the actual configuration. So remember, in the classical continuum mechanics, we operated with differential line elements, differential area elements, differential volume elements. And the basic trick or the basic idea was consider a very small line element at the beginning, very, very small. Enlarge it a little bit, but small, we write D, very small, very, very small. The length is going to 0. Okay? And in the actual configuration, if you deform the solid, the assumption was these 2 points are going to displace and this element can rotate and extend, stretch. So, but because it is very small, it was assumed it is very small in the classical continuum mechanics. The deformation or the motion is the rotation and stretch, elongation, nothing more, nothing else. So then you get dl. And then you may introduce many other quantities like the strain, stretch and strain. The strain was something like this, dl, dl0, dl0. Sorry. And so on. Okay. Remember, we introduced deformation gradient, displacement gradient, and so on. All of these quantities, like strain, at the end, they do not depend on the initial length, dl0. Remember, in 1D, the strain was du displacement, d is the displacement, over dx. In 3D, the strain tensor was 1/2 gradient u plus gradient u transposed. This is the classical continuum mechanics. Okay? Very good. We can solve a lot of problems, a couple of problems based on this. So again, go back. The very small line element, it is assumed that during the deformation, it can rotate and deform like a rod. The deformation is homogeneous. Okay? Therefore, we may introduce such a strain and so on. That was the basic assumption. Okay? The thing is, this assumption is not okay for all the problems. For many problems, it is okay. But if you have highly heterogeneous deformation, then you may have big problems with this classical continuum mechanics. Non-homogeneous deformation, what does it mean? Assume that you have this line element like a rod at the initial state, and you deform in the current state. You have not a rod, but your deformation is something like this. It may localize, it is non-uniform. The strains are not constant. Okay? So in this case, you still can say we have dl0 and this is dl. But this strain measure, or this approach, if you apply it, then you cannot see this heterogeneous deformation like nicking. The first example. The second example assumes that you have crack. At the beginning, no crack. And you deform the solid and the crack is formed. Okay? If you have already crack, if the crack is given, then you may analyze it by continuum mechanics, by the classical one. The so-called fracture mechanics was developed. But if you have no crack at the beginning, and the crack is formed during the deformation process, then you have some heterogeneous deformation. You have a displacement jump, okay? And this is another example. For this kind of problems, this approach is not reliable, the approach with infinitesimal line elements. Okay, and therefore, another approach is developed, the so-called peridynamics. And in peridynamics, you are working with finite line elements. Okay, that means you have at the beginning, you define 2 points. They are characterized by the initial vectors x and x prime. Prime is not the derivative. This is another point. Okay, 2 points. And you connect both of them and you get the so-called bond. This is the so-called bond. Okay, you may define the bond vector and so on. We discuss later this. And this bond formed by 2 points has a finite initial length. Okay, that means this is not dl, but this is some delta L0 at the beginning. There are no differential line elements. We might introduce them, but in PD we are working with bonds. And if you deform the solid, then these points you may have some displacements, rotations, and so on, and you have some finite length, delta L. This is not the differential one. So these are the same points in the actual configuration. Okay. Now you may introduce many quantities, and you may introduce the peridynamic strain that is specified by L. The definition can be similar. This is dl minus dl0 over dl0, or you may use any other one. The main difference that this is the so-called bond strain, but this bond strain depends on the initial bond. Okay, on the initial length. So this is one of the main features of the peridynamics. So we are working with bonds. Instead of differential line elements, we have bonds with finite length. So okay, what is the advantage? The advantage is you may have crack between them. Okay, it's not a problem. Okay, great. Now let us leave one page free for the notation. So notation. In PD. So we fill up this page during our derivations. Okay, so let us leave one page free. Now let us derive the balance of momentum. We consider the root, that means one-dimensional component, something like this. The cross section can be not constant, and let us assume small deformations. This is, in this case, we can use the coordinate x. We don't need x capital, x small. Okay. Of course, we can derive the theory for large extensions too, but to be simple to follow this. Okay, if you may subject this rod, you may apply the force F, or you may apply the distributed load, like the force of gravity, remember. That is specified by F small. This can be a function of x, some distributed force, like centrifugal force, force of gravity, the so-called body force. Remember this from the classical continuum mechanics. In PD, it is the same. Okay, the coordinate x is used to characterize the position of the cross section in the reference configuration. Okay. Remember how to derive the balance of momentum. First of all, we did this for part of the solid. For example, this one. Let's say this is the part P. of the solid. Then everything else in green will be called with R. This is the remaining part, or remainder of the solid. We consider the part P of the solid, and we derive the balance of momentum. So first, let me remember the classical continuum mechanics, the CCM approach, and PD is the same. The momentum, let us specify it by I for the part P. What do you think? Remember, the momentum is the mass times the velocity, yeah? First of all, you take this small part of P, like dx, and you say the mass is the density times velocity, density times dx times the cross-sectional area. A rho dx is the mass, and v is the velocity. And then this is the momentum of the small part dx, and then simply add. Add, that means integrate from x1 to x2, but let us abbreviate it. We integrate over the part P. This is the same as integral from x1 to x2. x1, x2 were coordinates of the part P. Remember this. Let us abbreviate. Okay? Great. So you may write it. This is the usual notation, integral over the part P of something. Dx over the part P. Some quantity like momentum. Okay. You remember this. We did this. So this is called momentum of the part P. The balance of momentum states that the rate of change of this momentum for any part P we formulate it for the part P is equal to the force, resultant force, and the resultant force includes two things. The first is the action of the environment in green. Remember, this is R, remaining part of the rod on P, okay? And we specify it now by this way. It is the force, this is the action from R on P. The force acting from R on P. Let's write it in our notation. A resultant force from R on P. Okay? So remember the definition, force definition mechanic. The force is a model for the mechanical action of the environment on some given solid. And this is exactly what we will. But we have another type of force, this small f, the body force. Let us specify it Fn on P. Okay? the body force, something like the force of gravity. Okay, so we discussed both of them in the classical continuum mechanics. Now let us recap how to compute this and that in the classical continuum mechanics. To compute this, you remove the part P from the root. Okay, and then replace the action of R on P on two sides, on the left and on the right. How to do this? Introduce, because we have 1D, we have tension or compression, nothing more, nothing else. Then the action of R on P may be only of this type. And we specified this by n of x2. Okay? On the left, n of x1. If you do not remember, please go back to the classical continuum mechanics. We had some lectures on this. x2, x1 are coordinates. So now this F R on P, this it was defined as n of x2 minus n of x1. So remember this. After that, we did the following thing. This can be replaced by the integral from x1 to x2 dn over dx. Or now with our new notation, we can write this is the integral over the part P dn over dx dx. F environment on P, this is the body force, which can be the force of gravity, multiplied by the mass. Let us assume that the mass is included in F. And this is an integral we have to sum up. This is the resultant force. The sum up is the integral over P. So this is all types of forces which are acting on the part P. This is f of x. And now the balance of momentum looks like this. Di over dt is the integral of P dn over dx plus the integral f of x dx. And then some inserted d over dt integral of P a rho v dx integral of P dn over dx plus f. Then put the derivative inside the integral, and then you have only one integral. This will be a rho v dot. Remember how we did this, applying the conservation of mass. So now this is minus dn dx minus f 0, and then localize it means if you say this equation is valid for any part P, which can be big or small, okay, then you say reduce this part, make it very small, and apply the mean value theorem. This is a mathematical approach to prove this. So that means from this follows that A rho V is dn plus dx n over dx plus f. So this was the equation of motion. CCM. See the lecture on classical continuum mechanics. Okay. Now let us do peridynamics. In peridynamics, there is a little bit different way to introduce the force F. Okay? Remember, the force F was called internal force in CCM. And in peridynamics, the approach how to define it is different. Okay? The difference is as follows. In CCM, you see here we introduced N capital at two positions. Okay? On the left and on the right. That means we assume that the environment R is acting on the rod by this way. These are two contact forces, and they are applied directly on the cross sections. In peridynamics, it is assumed that the internal forces are of the long range. Okay? So let us draw our rod again. And to introduce this long range action, consider two. So this is our part P, and this is R. So to introduce the action of R on P, first of all, let us look on the small part of P, like this. This is dx. And consider a small part, very small part of R. Say, this one. In peridynamics, there is a special notation. So the coordinate of dx is x as usual, but the coordinate of another point is specified by x prime. So, and this is the first example of the so-called bond. We have two elements, the x and the x prime. Okay, together they form the so-called bond. So this will be the x prime. And it is assumed that the x prime is acting on the x. They are on the distance from each other. Okay? So first of all, introduce the force. Now we have the action of R of the x prime on the x. Sorry. Applying our notations, we have the action of the x prime on the x. This is the force. Okay? And to introduce it, let us assume that we have the so-called bond force density. Let us specify it by n. N is the function of two things, x prime and x, because we have a bond. not just x. This is a bond for this force density. And after that, we simply write the length of the line element, dx prime, and dx. Okay. So let us go back to our notation and say n is the force density of the bond x prime x. Okay, if you know this bond form density, then you may compute the resultant force F, and this is the model which is the action of dx prime on dx. So this is in PD. Such functions, there are many, not just n, they are called two-point functions. Two-point function. We have 2 points. It's a bond, okay? Functions of this type are called two-point functions. There are many others, strain and so on, okay? They are defined for the bonds. Two-point function. Okay, let's go back. So now you see here, this is the main difference between CCM and PD. We have a small section dx, or a small mass point dx, and the point dx prime is acting on dx. They are on the distance. And the forces of this type are called long range forces. The classical continuum mechanics, the internal forces are contact forces. Okay? R is acting on P only in the contact point. Here is not so. This assumption is relaxed. Okay? Long-range forces in mechanics and physics is nothing new. There are many examples, like the force of gravity. Okay? Great. Now, if we have this force density, then it is not difficult to compute the action of the whole environment R, or the whole remaining part of the rod R on the X, on the small part dx. How to do this? I write this n x prime x dx prime dx and simply add all of them. Okay? Add, that means it's integral, and I integrate over, integrate over R. Yeah? That means I have the resultant force. This is the action of the whole R, of the green region R, on dx. And finally, we may compute the resultant force from R on P. How to do this? Because we have the action on dx, then we may compute the action on P, and we have to integrate over dx. Okay, and then we have the double integral. We write first this one over R and x prime x, let us write in colors. Oh, no. Colors dx, not this, dx prime. This is the first integral. Then it was the action on dx, and now we compute the action on p. That means I have to take the sum up everything over p. So now we have the force from R on P. And this is the main difference, the main feature on period dynamics compared to classical continuum mechanics. Now we have the resultant force in the balance of momentum Remember, we have di over dt of p for the part p, and now we have this guy this is related to internal forces, and we have the external forces, the action of the environment, and so this is the same as in the classical continuum mechanics. So this is the main difference, this guy. Let us derive some properties of this new guy in period dynamics. To do this, let us assume that we have statics to abbreviate everything. You may do the same for dynamics too, no problem. But if you have statics, then the left-hand side is 0. So the sum of all forces is 0, okay? In the statics, you have this F R P plus F environment P is 0. So this is FRP and this is F environment P, 0. Just to abbreviate, but you may do the same with the left-hand side. Okay? Now consider the root and assume that it was our part P. Now this equation is valid for any part. Let us assume that we have two parts, P1 and P2. They are connected together. So our P is the sum of the union of 1 and 2. This is specified as follows. Okay? The part P is the sum of 2. Now split the environment into, say, this is RA and this is RB. Okay? Now you can write the balance of momentum for P, for P1, and for P2. Okay? Let's do it. But to abbreviate, we write the statics, not the balance of momentum. So, for part P, let me use only one color. For the part P, it looks like this. It's already written. This is RP 0. For the part P1, here you have to say, okay, F R A on P1 okay, plus, this is the action of the guy on the left, but on the right, on P1, we have P2 and RB. They are both acting on P1. Therefore, here you have to write P2 together with RB on P1, yeah? And of course, the body force, environment P1. The sum is 0, yeah? The sum is 0. Let me move this guy to the left. Sorry. Zero. For the part P2, so now here you have, on the part P2 from the left, we have the action of RA together with P1. They are acting on P2, plus F RB on P2, plus F environment on P2 is 0. Okay? And after that, so if you say this is the equation 1, this is the equation 2, and this is the equation number 3. At home, do the following thing. Add 2 and 3, simply add, and subtract equation 1. Okay? And then use the property. Remember that the forces are additive. Okay? So homework, to understand this, do this, try to do this. Add equation 2 and 3, that means for two parts 2, 1 and 2. And subtract the equation of statics for the part 1. So after 5 minutes work, you need 5 minutes for this. But please try to do this. You get the following. You get that F of P1 on P of P2 on P1 plus F of P1 on P2 is 0. This is the principle of action and reaction. We proved them now. Peridynamics for the long-range forces too. Okay, this is the first property. The second property, if you assume that P1 and P2 is the same, for example P, then you get FPP plus FPP is 0. And or 2 times of this guy is 0, or from this follows that FPP is 0. Physically it is clear. This is the action of the solid P on itself. Okay? Great. Another proof. And finally, more and more important. If you take now as the part P a small guy, then and remember that F, for example, FPP is the density x prime x dx prime dx, but now you have the same PP, therefore you write XX, XX, this is 0. Therefore, the density XX, this 2-point function of this type, is 0. Okay? Now from equation 4, this is equation number 4. Insert instead of P2 x prime and instead of P1 x. Okay? From 4, you derive then n x prime x plus n x x prime is 0. Or n x prime x is minus n x x prime. So the force density for the bond has such an interesting properties. And in peridynamics, functions of this type are called antisymmetric. Okay? Let's go back to our notation. Right, let us write it here. So, and let us abbreviate. Let us specify by n and the function n of x and x prime. Physically, this is the action of x prime and x, yeah? Let us specify it by n prime. This is the notation in PD. And n plus n prime is 0, or n prime is minus n. And these types of functions are called functions with that properties are called antisymmetric. Of course, there are symmetric functions too in PD, not just antisymmetric. But the force density is antisymmetric because of equilibrium. So, okay. Now let us continue with some properties of this. Okay. Great. Now let us use these properties. Property FPP is 0. And now consider the union of the part of the body and the R, the remaining part. Let us abbreviate this by B, something like body, the whole body. So now, because FPP is 0, you may write that FRP is the same as FBP. Another property. It is clear because FPP is 0, okay, and the body includes both P and R. Then we have FRP is the same as FBP. So this will be numbered. This will be numbered. This will be 5, 5, This will be 6. Okay. Okay, another property from FPP 0. From this, we may derive a very interesting identity to remember this. FPP is the integral of P, and x prime x dx prime dx. And this is 0. The double integral over the same region of any antisymmetric function, remember, n prime is minus n, is always 0. This is another identity. Can be used later in period dynamics. 4. This is, of course, this is only valid for the antisymmetric function. Okay. And now the balance of momentum. Let's go back to the balance of momentum. This is d over dt integral over the part P. This is the momentum rho a v dx. The same as in the classical continuum mechanics. But now in the right hand side, we have an integral P, integral R, and x prime x dx prime dx plus the integral P f dx so now remember in the classical continuum mechanics to proceed we did a trick, a partial integration. Let's go back to remember. To proceed in the classical continuum mechanics we did this stuff. Therefore, we did a recap. So, remember, n of x2 minus n of x1 was the integral over p dn over dx. Okay? Okay? In PD, we do a similar thing, but not the same. We use this property. FRP is the same as FPP. And now, instead of this integral, we have P, and here I can write B, the whole body. So now, similar to classical continuum mechanics, in the left hand side, we have integral of P, and here we have the integral of P and x prime x dx prime dx plus integral over P f dx. Now you may introduce only one integral over P, and here you have rho a v minus integral over b n x prime x dx prime minus f, and everything integrated over dx, and this is 0. And now localize. This is valid for any p. Therefore, it can only be 0 if the guy inside is 0. And now we derived derive the equation of motion for PD. This is the integral over the body, the bond force density, dx prime, plus the body force like the force of gravity. So this is the PD balance of momentum in the local form. That means in the form which is valid for any point x. So this must be supplemented by the condition for n. We remember that n must satisfy this. So this is the balance of momentum in PD. What is the main difference? In the right hand side we have the integral. Okay? We have no derivatives. In the classical continuum mechanics, in the right hand side we had dn over dx, the derivative of something over dx. Here instead we have the integral. We have no derivatives. Okay? And this is the main feature, another feature of peridynamics. In peridynamics there are no special derivatives. Okay? This is instead of you have the integral of some force density. This has a big advantage if you have some very heterogeneous deformation, some jumps or discontinuities, okay? Then the derivatives are not well defined. Here you have no derivatives. Okay, now 2.3, power and energy. Why do we need power and energy in mechanics? First of all, power is important. Power there because there is different powers, power of external forces, power of internal forces, you remember. And if we have the power of internal forces, then we can introduce strain energy density. We have power variables force and strain, which are conjugate together. It's important in continuum mechanics. And therefore, we need this. Furthermore, in order to formulate boundary conditions, we need power of external forces. Okay? For example, if you have a constraint, some fixed boundary, remember, then the power is not supplied. It is important. Okay? From that condition, you may derive some boundary conditions. This is more or less trivial in the classical continuum mechanics, but this is not trivial in peridynamics. Therefore, we need to have a look on this in more detail. So 2.3, power and energy. So we start with the classical continuum mechanics with a recap. So, okay, 2.3.1. So 2.3, power and energy. 2.3.1, CCM, classical continuum mechanics, CCM. Recap. Okay, so again we have our 1D rod, something like this. It is loaded and we consider a part of the rod P. Remember last week, this is P, and everything else on the left and on the right is R, 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 and we have the environment from here there, because the force can be supplied from the outside. Okay, the part P has coordinates x1, x2, but we decided to abbreviate this. We take the integral over P. This is the same as the integral from x1 to x2, remember. Okay, now we derive the balance of momentum. And we got two forms for the balance of momentum. The first one was the so-called integral form. Remember, that was d over dt of momentum I for the part P, and this is equal to the total force supplied from the environment. And this total force was N of x2. This is the internal force supplied to P from the right, R, minus from the left, R, and all forces like the body forces, like the force of gravity or something like this. This is the so-called integral form. We derived it last week. I of P, this is the momentum for the part P, and this is the sum of momentum for all elementary part. This is the mass time velocity. Rho a dx is the mass, v dx velocity. Okay. This is the integral form. That means this is valid for any part P. Or the local form in CCM for any x. Yeah, you can do some transformations and localize, and you get rho a rho v dot, the rate of change of momentum, and here you have d normal force over dx plus f of x. So remember. Now let us derive the so-called power identity and kinetic energy identity in classical continuum mechanics. Let us recap how to do this. Take this local equation in the local form and multiply the left-hand side and the right-hand side by the velocity. Okay? So multiply by v. Then you get a rho v dot v is dn over dx v plus fv. This on the left could be written as a rho d over dt and this is v power 2 over 2 v dot v. Okay, and the right hand side, this guy could be written as d over dx n v minus dn minus n dv over dx plus fv. So some elementary mathematical tricks, but they are very important. Okay, now let's do the following thing. Let us integrate the left hand side and the right hand side over the part P, or from x1 to x2. So if you do it from the left hand side, you have this a rho d over dt v power 2 over 2 dx, and here you have integral over P d over dx and v dx minus integral over P and dv dx plus this guy, the last one, f v dx. Okay, now let us proceed step by step with this. First of all, the left-hand side can be transformed, so the left-hand side, such that we get d over dt k of p, where k of p is the kinetic energy of the part p. So how to transform? Do it at home or open our lecture on continuum mechanics. You need conservation of mass to apply and so on, okay? So k of p is simply the integral over p, the sum of, and inside the integral we have the kinetic energy of the elementary mass point. This is, so a rho dx is the mass, okay? And the mass times velocity power 2 over 2 is the kinetic energy. So a rho dx is the mass, okay? The sum is the integral. So this is the first step with the left-hand side. Now let's look on the right-hand side. We have several terms. So let's take this guy. So this guy is integral over p d over dx n times velocity, and this can be integrated because the derivative over dx, okay? And then we have nv with the integrational limits on the left and on the right, and this was x1, x2. So this is n of x2 v of x2 minus n of x1 v of x1. So what is it? So the force times the velocity is called power in mechanics, yeah? And this is power supplied from the environment on the left and on the right cross section into the part P, okay? This is the power supplied into the part P from the left and from the right. So let's write it. Power supplied. Let us abbreviate it. Let us write L, not P because we have already P, but in Germany power is Leistung and usually it is written by L. Okay, L supplied, and we should designate that this power is supplied from R into P. Let's write it by so in our usual style. Similar to the force. We introduce the force from R to P. Now this is the power from R to P, okay? Great. This notation was not used in classical continuum mechanics, but to understand periodynamics we need it now, okay? Great. So the next guy. Let's take this one. This one. This one is easy. We have nothing to do because F small is the external force, something like gravity. Okay? Now this is multiplied by V, by the velocity of one point. And the sum is the total supplied power from the environment. Okay? So this integral f v dx, again, this is supplied, but let us write environment because here is this is the power from the environment on P. Okay, and finally we have this guy. Remember, we have minus before, but I write it without minus. So n times dv over dx. So, sorry, integral n dv over dx. What is it? To understand it, remember that in the classical continuum mechanics, so v is the time derivative of the displacement, the velocity. And the u over the x, you remember what is it? Gradient of u. And what is it physically? Strain. In 1D, it is strain. It was designated by epsilon, yeah? And therefore, this guy, so you can show this by the geometrical way, that du over dx is a strain for the rod, okay? And now this guy is simply n times epsilon dot and the sum up over all x, okay? This is n is the internal force and strain dot is the rate of strain, yeah? And this is called power of internal forces. Remember, this is the important thing. This power can be stored as the strain energy, or it can be dissipated. Many things are possible, partly stored, partly dissipated in the case of plasticity. So, but anyway, N is the internal force, and this is conjugated with strain rate, with strain. Therefore, any constitutive equation in mechanics relates the internal force N to the strain. Okay? Or in 3D, remember the stress tensor was introduced. So, okay, we can specify it by L again, but now we write not supplied. This is not supplied. This is the power, we may say, the power absorbed. And in the part P, because it's the integral of P. Power absorbed in the part P. Power is supplied or absorbed. So it can be stored as the energy, or it can be dissipated. Dissipated, you remember what is it? So the heat. Okay. All right. Now we derived the so-called energy identity. Nothing new. We used only the balance of momentum. Here's nothing new. And after some transformation, the so-called energy identity. The rate of change of the kinetic energy for any part P, this is minus L absorbed of P. Remember, it was minus before the integral, plus supplied power from R to P, from the left and from the right into P, supplied, okay? And supplied from the environment. So all of these guys are defined. This is the energy identity. This is not the balance of energy. To get the balance of energy, we need to proceed and to define the absorbed power in terms of the strain energy or internal energy density and so on. Then we get the balance of energy. But this is the identity, okay? It's derived from the balance of momentum, nothing really new. But we need this in peridynamics too. Why? In order to define the powers, okay? Here's everything more or less trivial. Okay, I hope everything was okay. Now let us proceed with peridynamics. So to do this, we start with balance of momentum. So this is 2.2.3.2. Now we have power and energy for PD. PD is peridynamics. So, but remember, we derived the balance of momentum in PD. Again, two forms. The first form is called the integral one. The left-hand side is the same as in the CCM, the rate of change of momentum. But in the right-hand side, we have something different. We have no derivatives, but we have a double integral. And here we have the part P. And here we have R. This is the force acting on P from R. And this force is the sum of densities and x prime x, dx prime dx. Dx prime dx are two elements. One, dx is in P, dx prime is in R, okay? And they interact because the force is of the long range. And plus we have this guy, this is F dx. This is the same as in CCM. Remember, this guy was called the force supplied from R into P, and this is the force supplied from environment into P. Okay? Okay. So in the local form, the local form looks like this. I guess after some transformation and localize, we got local form. That means for any point x. This was for any part before. This is for any point x. So this is the integral over the whole body, and x prime x the x prime plus f of x. And remember, this body was the part P together with the environment R. This was derived, and it should be supplemented that the n, the 2-point function, is antisymmetric. So this was the balance of momentum in the local form. So now let us proceed with the power and energy identity. We do the same. Multiply the left-hand side and the right-hand side by V. Okay? V of x. Now you get rho A 1/2, the same as before, d over dt. V power 2 over 2. In the right-hand side, because V depends on x, and the integration is done over x prime. Okay? We can insert it inside the integral. So we get B, and x prime x times v of x dx prime plus f of x v of x. Okay, great. Then the next step, integrate the left hand side and the right hand side over p. We do the same as before. So integrate over p, integral p of this guy and this guy. Now let me skip the arguments to be short, okay? And this guy okay? And now the left hand side is the rate of change of the kinetic energy, the same as before. In the right hand side we have this guy, double integral, and this guy is introduced before. This is the power supplied from the environment. Just a moment. Dx prime dx, yeah? Dx, so yeah, dx prime dx, double integral dx prime dx. Okay. So do not remember that n plus n prime is 0. It should be the condition and the additional condition. Okay, that belongs to the balance of momentum. So okay, now we have this guy, this power, and this should be, remember what we did before in CCM. We used so mathematical operation, which was the integration. First of all, we splitted this in the sum of two parts, okay, and then we integrated one of them. By this way, this guy, from this guy we got two: the power supplied from R to P and the power of internal forces. Let's try to do the same here. So let's try to do the same. What we do now is derived in our group and published, okay? But maybe you can find another way. NV, so the approach is very simple. This power NV can be reproduced as the sum of NV plus N prime V prime, okay, plus 1/2 NV minus N prime V prime. Nothing really new. So add and subtract N prime V prime. Okay, this is the first step. Now take into account this, that N plus N prime is 0. Therefore, this is 1/2 NV minus NV prime, okay, plus 1/2 NV plus NV prime, okay, because N is antisymmetric. N is antisymmetric because action is minus reaction. Okay? So, great. Now, let me write it so. Let me write minus 1/2 N V prime minus V. And this is 1/2 N V prime plus V. So remember, V prime is the velocity of the point x prime, and V is the velocity of the point x. Okay? Okay, so continue. Now, let us specify this guy by small l. And let me write LA. Later we show, or we assume that this is the integral over this, will be the absorbed power. This guy by small ls. First of all, let us show that LA is symmetric. To do this, take prime. LA prime, this is 1/2 instead of n, write n prime instead of v prime. V prime prime is v and minus v prime. Okay? But n prime is minus n. Therefore, this is minus 1/2 n v minus v prime, or this is 1/2 n v prime minus v. And this is LA. So LA prime is LA. Okay? Great. Now let's do the same. So LA is symmetric. Now let's do with L supplied prime. We have 1/2 n prime. Here we got v plus v prime, or this is minus 1/2 n v prime plus v. Okay? And now we see that ls prime is minus ls. So this guy is antisymmetric. Okay, now let us look until we have to integrate this, because these small l's are inside the integral PB. Okay, now we have the integral P, the integral B, n times V dx prime dx. This was introduced as a sum P B with minus before L absorbed plus P B L S. So LA and LS are defined before. LA is this guy. Remember minus before, but we introduce it as 1/2 n. Oh, let's write it again. So let's write LA is 1/2 n V prime minus V, and LS 1/2 n V prime plus V. Okay. Okay, first of all, let us consider this guy. Integral P B L S dx prime dx. And now let us do the thing which is similar to the integration before in the classical continuum mechanics. We split this integral into the double integral pp ls dx prime dx, and because the body is p plus r, this is p r ls dx prime dx. Okay, yeah. No, LA is positive, but here we have minus before the integral. Okay, LA is n 1/2 n v prime minus v, minus before the integral. What is the question? LA prime, you take this with plus 1/2 n v prime minus v, take n prime, okay, v prime and prime is v minus v prime. I took simply the prime of the whole stuff. Okay, sorry, here is minus and here is plus. Here is plus, here is minus, but then I need v prime minus v, so this is plus. LA prime is LA, okay? But LS prime is minus LS. This is important. This is important. LS prime is minus LS. Remember last week, go back. I show you there was one important relation, this one. For any antisymmetric function, the double integral over pp is 0. Okay? Physically, that means in the case of n, this is the action on itself. So it's 0. Now we have the same with the power. Supplied power, pp. The supplied power is antisymmetric, and this integral is 0. And now we got the similar thing to the classical continuum mechanics. Here we got, remember, this guy, and it was possible to integrate it over p, and we got the power supplied from the left and from the right. So in CCM it was at x2, x1, yeah? In PD the action is non-local. Therefore, we get something different or generalized. So this guy is 0, and therefore the result is only this term. And we got the power supplied from R into P, from the left and from the right. This is the double integral P R L S dx prime dx. Or let's write the final result in red for us. From R into P, this is the power supplied from R into P, and LS is 1/2 n v prime plus v, yeah? I inserted back. So this is the power supplied through the cross, not the cross section. We can see cross section from the right and from the left, from the environment. Okay. Okay, and now the power absorbed. Let's write only one argument. It's enough. This is P, but the integral of the whole body, and this is 1/2 n v prime minus v. So we may say that this has a sense of the absorbed power or power of internal forces, okay? Yeah, and this is the power supplied. Finally, we get the same identity, not the same, the identity is the same, but the meaning of terms in the identity is different. So let me write it again. The same identity as in the classical continuum mechanics. K and of P is the same, but the meanings of powers is different. LA and LS are different in PD. Okay? So we could show that we got the same. Let me write it again in PD. In PD, we have d over dt k of P is minus, remember it was before the integral, L absorbed plus L supplied from R into P and L supplied from the environment into P. And the meaning of terms of these two guys, LR, let me write these two guys in red to underline that the meaning is different. L absorbed and L supplied. Everything else is the same. Okay. So now why do we need them? Again, in the classical continuum mechanics, let's go back, the supplied power from the cross section, this one. Oh, you see here, N times V. It is important to use to formulate boundary conditions. And they are formulated for N or for V. Better say for U, okay, for displacement. If you have the constraint, then U is 0, V is 0. The power is not supplied, okay? Or if you have a free boundary, then V is not 0, but the force N can be supplied as F, and you get power. Or if you have a free boundary, no forces are acting, then the force is 0, the power is 0. It was very easy. Remember, in finite elements, click on boundary conditions. Oh, it was degrees of freedom, U or force, okay, at the point. In PD is a little bit different. You see here we have the integral, and so the integral is supplied. You have the environment, okay, and you have the power supplied from the whole environment on the left and from the whole environment on the right. So there are no specific points. We discuss it later, how to formulate boundary conditions, okay, in peridynamics. But the power is very important. Without power, it is difficult, not so easy to say what we have to apply, okay? We may say, for example, if we have constraint, then the power should be 0 in PD, okay? Then we set Ls to 0, okay? Great. And regarding absorbed, this is the power of internal forces. Yeah, we should proceed with the strain energy and density constitutive equations and so on. In CCM, remember, and here. Okay. And the next point is 2.4 constitutive equations. 2.4. We start today with the constitutive equations. And remember, constitutive equations is a big topic even in the classical continuum mechanics. Of course, we have no time to present all possible constitutive equations for all possible materials. We limit only for some examples. And let us start with CCM 2.4.1, CCM, and how to formulate the constitutive equation. First of all, remember that the absorbed power for some region P, a part of the rod P, it was the integral in CCM, the internal force N times, so N is a function of X is the cross section of the rod, times the strain rate of X. X is a cross section of the rod, and the strain was du over dx. U is the displacement. Yeah. Remember from the continuum mechanics course how to formulate the constitutive. First of all, we see that the power of internal forces for any x is the product of N and the strain rate. That means the force N, you can say this force N is power conjugate to the strain, with the strain rate. And therefore, the constitutive equations relate the forces and the strains or strain rates. So we see that in this theory, we should relate N with the strain or the strain rate. And this is the constitutive law. But now, before doing so, let us remember that for some materials, the power, the absorbed power of internal forces, is going to change the energy. And in this case, the forces, so let us define the energy, which is in general the internal energy, but in the case of elasticity, this is simply the strain energy of the region P. This is the part of the rod P. This is the integral of the strain energy density dx. So E is the strain energy, let's write energy density, internal energy density. Or let us write strain energy density, okay. Okay, so now if you introduce this and say that the power of internal forces is going to change this energy, that means the rate of change of this energy for P is exactly equal to the power of internal forces. Then we say in mechanics, we say that in this case, the internal forces are conservative, or there exists some potential. The potential is this strain energy density. Or in this case, you may the same, of course, this is E dot minus N epsilon strain, and strain dx is 0. And the localized condition, it is clear because it is valid for any P. You write epsilon, E is N epsilon dot. Okay. So the internal forces of this type are called conservative. So, okay, and then if we say we have elasticity, then of course one example for conservative force N is the force related to epsilon by the elastic law. So N is a function of epsilon, and the elasticity means so it can be linear or nonlinear. That if you start here and go lowered and then unlowered, then you go back. So there is no dissipation of energy, and in this case, N is the function of epsilon only. This is one example of the conservative force, the elasticity. So, or the elastic force which satisfies the elasticity relation. This case, the strain energy density, of course, this is a function of epsilon only. And then you may immediately derive, so E dot is then, sorry, E of epsilon. This is the E over the epsilon dot. And if you introduce this into this relation, you get N minus dE the epsilon dot is 0. And because this is valid for any epsilon dot, N force is defined by the potential. So, and if you say N is the linear elastic, so the behavior is linear elastic, N is some constant C times the strain, then you may find out immediately that the strain energy density is then 1/2 C epsilon power 2. So this was discussed in the classical continuum mechanics. Remember, this stiffness constant can be identified from the, if you apply the tensile test, then you get the following constant. This is the Young's modulus times the cross-section area. So in the case of tension or compression, you have this relation in the classical continuum mechanics. So this is the Young's modulus. And A is the cross-section area. Okay. So this is in the case of elasticity, and yeah, many materials have this elastic regime, but in many cases you observe inelastic behavior. This may be plasticity, creep, damage, and so on. In this case, this equation or this is not valid anymore, and generally only a part, as not all the power, is conserved or converted into the rate of change of some energy. And the more general relation looks like this. You have d over dt of the strain energy, and this is not equal to the power of internal forces. Let's write it a little bit in this form. So let LA some region P is the power of internal forces, and in the general case the difference is not zero. So if you subtract the rate of change of the strain energy density, then this is not zero, but only a part of the power is converted. So this difference is not negative. In this case, we speak about dissipation. Dissipation. One part of the mechanical power dissipates or can dissipate. You may introduce the dissipation d if you want for the region P. And this is the definition. This is LA minus the rate of change of the strain energy. This is a non-negative quantity. Remember, in the general case, we discussed it in CCM, you have to work with thermodynamics, continuum thermodynamics. Then you introduce the temperature, entropy, and epsilon is the internal energy, or in some cases, this is a free energy. So, but if we limit only to mechanics, if we skip thermodynamics, if you say temperature is constant, for example, the process is isothermal, then epsilon is a pure mechanical component. We don't need to work with temperature and entropy, and this is the dissipation inequality in mechanical theories. Okay, great. This is an example, or the first very simple example of the constitutive equation in CCM. Later we may extend it, but now let us first let's try to do the same in peridynamics. So 2.4.2 peridynamics. Let's do the same. Let's start with the supplied, not supplied, but absorbed power for the region P. And this was a double integral. This is our region P, but this was P plus environment B, and here we got 1/2. So we define it as small LA x prime x dx prime dx. And in the last lecture, we observed, or we introduced this small LA, and it was 1/2 n x prime x times the velocity at the point x prime minus the velocity at the point x. Okay, so now we observe again that we have a force quantity, this one. We have the bond force density, and this is the power, elementary power for the bond x prime dx. And now this force is power conjugated with the difference in velocities of two points, x prime and x. And now, if you remember that the velocity is the time derivative of the displacement. So we have 1/2 n x prime x. Here is the displacement dot. Dot is the time derivative as usual. Or you may write it so. Put the time derivative before. And let me skip the arguments to be short. This is the time derivative. And now we have u prime minus u. Now you see that this n is power conjugate to the difference, to the time derivative of displacements, difference of them. And this is a peridynamic deformation measure, u prime minus u. So we may immediately say that the constitutive equations should be formulated as relationship between n and u prime minus u. Okay? So this is the first what we can observe. Remember that this n must satisfy the following relation. So n prime plus n is 0. It is always to remember, or n x prime x plus n x prime is 0. So to avoid this, it must be always included this equation. In peridynamic literature, another quantity or another bond force density is introduced. So usually the notation they use is T small or T capital in 3D. They introduce another quantity, Tx prime x, another function, as follows, such that the n is defined as follows. Nx prime x is T x prime x minus T x x prime. So if you look into the peridynamic literature, in many papers, they operate with the T. And now, if you use T, this T function, then this equation is satisfied always and automatically. You may prove this. Or abbreviated, you may write n is T minus T prime. So therefore n prime is T prime minus T, and therefore always with this T, n prime plus n is 0. Now, in the PD literature, we have now different force densities. This n is called dual force density. While this P is called force density, bond force, sorry. Dual bond force density, and simply this is simply bond force density. Okay. Anyway, you may call these two densities. So, to remember this, let us go back to our notation page, to the beginning. It was here, it was our notation. Where is notation? PD. So, n x prime x is called dual bond density, while T x prime x is bond force density. So this n relation is between them. N is T minus T prime. Why do we need it? To satisfy this condition. Okay, but it is not really mandatory to introduce it. You may work with n, but if you work with n, then you have always remember n plus n prime is 0, that n is geometric. Okay, so let's continue. Okay, great. If you work with the bond force density, then this LA looks as follows. Let us insert LA x prime x will be. I insert in state t, and I have 1/2 t minus t prime. This is n. And here I have v prime minus v. Now this is 1/2 t times v prime minus v. Now let me write plus here instead of minus 1/2. But instead v prime minus v, I write v minus v prime. And then I get the following. I get two terms. Let me specify the first one by LAT. And this is this guy. While the second one, see, this is simply the first one primed. Or prime is the same function, but for x prime. So if you work with t, then the LA, the elementary supplied power for the bond, this is LAT plus LAT prime over 2, some mean value, while LAT is simply t multiplied with the velocity, difference of velocity. Again, you see that this t is power conjugated with the rate of change of u prime minus u. And we can formulate the constitutive equations for t, and t should be related to v prime minus v. Okay, let's try to do it again. First, assume the elasticity, or in other words, that the bond force density are conservative. In this case, you may introduce again something like the stored energy, which can be the strain energy for the part of the rod P. And here are the following possibilities. First, you may introduce the peridynamic strain energy density. Let me write E with bar to distinguish from CCM, because in general case it is different. As a function of x dx, this is the density. Or you may introduce the bond strain energy density. If you deform the bond, the energy in the bond can be stored. And let me specify the bond energy density by EB. So EB, now we have the integral over the part, and then the integral over the body, and EB is introduced as follows. So then I have to write EB plus EB prime over 2 dx prime dx. So let me call EB. So E is the strain energy density, and EB is the bond strain. strain
Hello.
energy. Okay, so okay, and now so now let us say that our internal forces are conservative. That means the rate of change of this epsilon p should be equated exactly to this LA capital of P, okay? We do the same as in classical CCM. We equate, we have no dissipation, then LA is equal to epsilon P dot, or epsilon P dot can be equated to this. So epsilon P dot, or the rate of change, is LA. That means we have elasticity, okay, or something like this. Then if you insert, then you have one version, the integral of P. Remember, this is our E, strain energy density. Now subtract the the integral of over B, 1/2 m d over dt u prime minus u dx prime dx. This is 0. So the strain energy density minus power of internal forces looks a little bit more complicated because n is long range. Or if you work with t, then you may write the following thing: p, and now the integral of b. Here we have E bond rate minus T d over dt u prime minus u dx prime plus the same but primed eb minus t d over dt. Let me write this on the next line. It's better. Minus t d over dt u prime minus u. Let me write it so to abbreviate. Everything is primed. So the integral, close the integral. Now this is dx is 0. Okay. Okay. Or you may write the local form. If you say this is valid for any p, localize, then remove one integral. You will get e small bar prime is equal to this one integral over b 1/2. Or here you get this relation, eb integral over the body, eb minus this guy is 0. So, okay, this will be the condition for conservative forces. It means the power is going to the power of A of internal forces can be equated to the rate of change of the strain energy density. Okay, now let us define constitutive equations. In contrast to CCM, we got only one linear elasticity relation. This was because M capital is a function of x only, 1 point. Okay? So there was only one possibility, n is some constant times the strain. Here it is not so, because this n small or t small is a function of the bond. It is a two-point function. Therefore, it can be related to the difference of displacements and to the difference of coordinates. Okay? The first step, so t or n, let's write t, is in general a function of u prime minus u and x prime minus x. This is in the case of elasticity. Yeah. This is the difference. Okay. The first step to proceed is to think about the long range action. So we talked about the long range. The question is how long this range could be. And in pyrodynamics, the first step, what they do is to introduce some kind of the cutoff of this long range action. That means the dependence of x prime minus x is restricted as follows. We say that this t or n is equal to some function, let's say t delta, another function. So, sorry, x prime comma x. If the length of x prime minus x, the bond length, is less than some quantity, which let us write delta for this. This is the usual notation of pyrodynamics. And otherwise, it is zero. So this delta in pyrodynamics is called horizon. So what is the meaning of this? Remember, we have our root, looks like this. And now if you have the point x, okay, and you have this, the element at x, then you say simply this element can interact not with the whole body, not with the whole rod as assumed before, but only with points inside a small region, this one. So, okay, and this is delta, and this is delta. So outside this region, the interaction force is zero. And this is exactly what we have written here. So in pyrodynamics, delta is called horizon, or the value of delta is the horizon size. Okay? Great. This is the first step. What we can do, we can fix or cut off the range of action of the force T. In the next step, we can do something like elasticity. And there are many different possibilities how to define this function. Let us write the first example. The first possibility. Let me write t x prime x by the following way. Let me write some constant c, again some stiffness as before. Then some function of the bond length, say omega of the bond length, And then we can multiply this by the difference in displacement. So this is u of x prime minus u of x. So the first example. So this is the stiffness or bond stiffness. This is some kind of this function describes how this T is acting over the bond length. It can decay, for example. You may use here something like the exponent or even the constant is possible, but in general it can be the function. Let us call it influence function. And this u prime minus u, this is the PD deformation measure. Why? Because T is power conjugated to the rate of change of this. So therefore we write it so. This is one example. And of the constitutive equation in thermodynamics, maybe the mostly simple example. Okay. What we observe, the bond force density of the bond x prime x depends only on the bond deformation of the same bond. Other bonds do not have influence on this. And this is called, in thermodynamics, a bond-based theory, bond-based theory. Again, this force or the bond force density of the bond depends only on the deformation of that bond. There are more complicated theories where you can say that the bond force density of this bond depends not only on this deformation of that bond, but other bonds of the bond family connected to X have the influence on that force. And theories of this type are called state-based, but we discuss it later. Let's start with the simple one. And first of all, let us introduce the so-called bond strain. To analyze the deformations, let us introduce the bond strain. Again, consider our rod in the reference configuration. This is our rod in the reference configuration. And consider this bond, for example. This is the point X at the beginning. And the second point is X prime. For example, this one. Okay, let's define the initial length of the bond, L0. L0 is x prime minus x, of course, the absolute value. Why? Because x prime can be on the left of x as well. So in PD, this x prime minus x, sometimes abbreviated by xi. And in this case, this is the absolute value of xi. In thermodynamics literature, xi is used for x prime minus x. Or in 3D, this is xi vector, because x prime and x are vectors. In 1D, we have this xi simply, scalar. Okay, now let us deform the root. Deform. And deform. That means in the actual configuration, it looks something like this. And this point, let me take the red color, is going to move to the right. So this will be our point x in the actual configuration, and the point x prime is going to move something like this. Now remember that this in mechanics is called displacement. Okay? In 3D it was displacement vector. This is a vector which connects the initial position with the actual position of the point. And now this is u prime. This is the displacement prime. These quantities were introduced before. They appear in the power or in the work or in the constitutive equation. So let us look at them. First of all, let us compute the actual length of the bond. So that means this distance. Okay? How to do this? Remember that this one, from the picture, you see that this position is a point x prime plus the displacement u prime. While this point has the position, the actual position x plus u. Now this red length, the actual length of the bond, is take the right one, x prime plus u prime. Subtract the left one, minus x minus u, and take the absolute value because the length is always positive. Okay? Great. Let me abbreviate. So you see here, we may write it so. This is u prime minus u plus x prime minus x. X prime minus x was abbreviated by xi. Now we may write u delta or something like this. Now it looks shorter. U delta is simply u prime minus u. Okay. Now you may introduce the so-called bond strain. The definition of strain, you remember, is still the same, but let us write B. This is the bond strain. This is the actual length minus the reference length over the reference length. The same definition as in the classical continuum mechanics. But now we are working with the finite length of elements. This is L0. In the classical CCM, we considered only the infinitesimal elements, okay, and computed the strains. Here we are working with bonds, and now we can compute the bond strain. So the actual length is u delta plus xi, okay, minus the reference length is xi, or the reference length is xi, the absolute value. Or you may write it so, u delta plus xi over xi minus 1. Okay. This is the definition of the bond strain. The definition of the bond strain. Now, the following things should be taken into account because we are working with bonds and the length is L0, the initial length. It is clear that the epsilon b depends on the bond length. We see here this function of psi. One thing to be considered is the following. Assume again we have these bonds at the beginning, this bond XX prime, okay? And now assume that you subject the rod to compression. Compression, that means the strain will be negative, but we cannot infinitely compress. At some point, we can observe this, that the points are in contact. Sorry, x prime. But we cannot imagine that these points are penetrating in each other. This is non-physical. Okay, and therefore the condition also no penetration. The condition is that the actual length is not zero, yeah? So we can write it, remember in CCM, we had that F not negative. The deformation gradient was not singular, and the condition for this was important. Remember that F was the change in volume dV over dV0, and it means dV is non-negative. This is physically clear. Here's a similar. We can formulate it. The actual length is U delta plus psi. Is it correct? Yes, absolute value is non-zero. Or you may write it so, non-zero, that means that is clear that it is positive. You may write it in this style as well. So now if you analyze this equation, I keep this homework. Please analyze this and so homework show. So I did it, and my result is that show that from this non-penetration conditions, the formula for epsilon b can be simplified as follows. So from this condition, you get a very simple formula, U delta over psi, or U prime minus U over X prime minus X. So, but of course, we have always to remember, we have always to write it that U delta plus psi should be positive. Okay, now we have introduced this strain, the bond strain, and now we can formulate the constitutive equation, the elasticity constitutive equation, in terms of the bond strain. So simply take this and replace u prime minus u by the bond strain. Then you get the bond strain times x prime minus x. Okay, and then you have T, the bond force density is then some function of the bond length multiplied with the bond strain. Okay, now please try to think about this condition, and at this point I would like to finish. We are going to continue next week. So, first of all, remember the bond force density T for the bond x prime x. There are two steps. First of all, we introduce the cut-off side, this whole called horizon. Okay? Outside the horizon, the force is zero, no interaction. If the bond is outside the horizon, imagine you have a bond, this is x, and this is x prime. This is our bond. So if this bond length, x prime minus x, is the bond length, only if it is less or equal delta is the horizon, we have interaction outside zero, cut off. Okay, so, but what is going on inside? We found out that we may assume that this function of x prime x is a product of two functions. One is the function of the bond length, some omega. And so here we might write some stiffness before. And based on the energy and power, we found out that this bond force should be proportional to u prime minus u. This is the difference between the displacements, or relative displacement. Okay? So this is if x prime minus x inside the bond, inside the horizon, zero otherwise. Okay? Okay, what is the meaning of this? First of all, the relative displacement. So, if there is no relative displacement, the force is zero, like a spring, okay? Second, this function omega says that the force is not constant, or can be in general not constant. If we have this bond, okay, for example, then if we increase the bond length, then the interaction should decrease, okay? So if the distance is small, it should increase. It is clear to understand. The long-range force, you may imagine some kind of force field, okay? If these points are close together and you try to put the displacement, then you have a feeling on some kind of reaction, okay? And this reaction is strong. But if the points are outside of each other, distance is quite large, then try to displace no interaction or very small interaction, okay? And this is included inside this function omega. Of course, we may imagine many different examples. And this is one part of the constitutive equation, this type of decay, okay? It's a property of the force field. But there are some examples. This is our publication in a journal, our recent publication. There are some examples. You may imagine a constant interaction and then cut off triangular this type with infinity, or this type, something like Gauss. Okay, curve. We imagine many other examples. Let me take this one because this one is the mostly used in the literature. So this one, omega. So let me abbreviate this. X prime minus x is psi. This is another property of the constitutive model. Okay, omega, c, and horizon are properties of the constitutive model. We discuss later how to identify c, how to set the horizon. The horizon must be small, but how small is a good question. Yeah, we can discuss it later. So now x prime minus x, abbreviate by xi. And one example for omega, very simple, is 1 over absolute value of psi. That means it looks like this. So at some point x, it is going to infinity, and then it is going to 0, and this is your cut-off horizon. So it looks like this, okay? So for infinite horizon, it tends to 0. This is one example. So this is psi, this is 0. So something like this. See, this type of function is widely used in the literature on polydynamics. Okay, then everything C, we identify C, the stiffness later, and we discuss about the size of horizon later. U prime minus U is the relative displacement, okay? Then remember we introduced with last week the so-called bond strain. Bond strain is a two-point function, is a function of the bond, and this is the relative displacement over x prime minus x. So you may observe that this function is symmetric, yeah? Because if you take, it is clear physically, this strain for the bond x prime is the same as the strain of the bond x prime x. Exchange the points, get the same strain. Okay. Okay, now because epsilon b, you may write it as a function of x and psi. If you change the variables, then you get u prime minus u over psi, yeah? And now you may formulate the constitutive equation for t. So t is now, let me skip this if, then it is clear that we are only inside the horizon. Now we have simply c u prime minus u over the absolute value of psi. Now very simple constitutive law, maybe the mostly simple. So c is the stiffness 1 over psi is omega and u prime minus u. Everything inserted. Okay? Now you may formulate the same in terms of the bond strain. To you remember the classical elasticity law, stiffness times the strain. Okay? Now write simply the bond strain. But here we have psi, and here we have the absolute value of psi. So I have to multiply by psi, absolute value divided by psi, yeah? Then it is the same. But this is nothing else, that's SGN psi. Okay? Therefore, now we have one example of the constitutive law. X prime x or x psi, let's write x prime x, then this is C, the bond strain x prime x, SGN, this is the direction, okay? X prime minus x. Or in terms of psi, T x psi, so I replace x prime by psi. This is x psi SGN psi. This is another type of formulation. So the first one tells this is a function of the bond x prime x, while the second one tells us we are at the point x, okay, and psi is the local coordinate around x. Okay, regarding the bond strain, what is the advantage of this? One interesting thing is to remember that the formulation is valid for any bond length, yeah, inside the horizon. Now let's check what is going on if we assume that the bond length is very small, extremely small. Then you have to take, so what will be with epsilon b? You have simply to take this guy for psi to 0, u prime minus u, x prime minus x, or x prime minus x to 0 better. What is it? The derivative, yeah? This is du or dx. Of course, please remember the assumption should be made. U is continuous, so you can take the derivative. So sometimes you may work with discontinuous functions too. You have a jump, the Heaviside function, the derivative of Heaviside is delta function, yeah? It's possible as well, but in the classical analysis, you should be continuous. Then you may take this reduce x prime minus x, and you get this derivative. But this is the classical strain, okay? And therefore, the bond strain in PD is going to the classical strain if the bond length tends to 0 and u is continuous, okay? And therefore, it is convenient to work with this formulation, including the bond strain. Okay. So how to find C and how to fix delta? There are now only two parameters. This question should be discussed later. This is the question of identification of material properties, yeah? But before doing this, let us formulate the equations of peridynamics, final equations. Then we discuss how to solve them. And then we consider some simple problems like tensile test, analyze in PD, and in tensile test, we apply the force and measure the elongation. And from that, we can get C, maybe C and delta, maybe only C without delta, okay? This is the basic approach in all continuum mechanics and in peridynamics too. Okay, now 2.5 equation of motion. It was 2.5 as I remember, yeah? PD equation of motion. actually we derived already this before, but in the general form. Look, before it was rho a u dot dot or v dot. Okay, this is the rate of change of momentum for any point x. And in the right hand side, we got the integral over the body. It was nx prime x, the x prime, plus the body force. I think it was so. We did this in our first lecture. This is the peridynamic equation of motion. Now, in this form, we cannot solve it because n was undefined. Now we have to apply the constitutive equation for n. And now n was t minus t prime. Remember, n is the dual bond force density and t the tier bond force density. And for t, we have now the constitutive law. Okay? Okay? Therefore, the integral over b, t minus t prime, the x prime, is now the first step. Is to remember that we had a cut off. Okay? Therefore, from the whole body, we have only a small region inside the horizon. Everything outside is zero because t is zero. Okay? Therefore, instead of this, we have x minus delta, x plus delta. Now we have t minus t prime, the x prime. Now you may insert t. T is given here. T. Where's t? Here is t. Okay? Let me copy this. So then t prime is nothing else than t exchange x and x prime. Here you remember we have the same because epsilon b is symmetric, but sign x prime minus x will be minus. So SGN x minus x prime. So let us write it. SGN. Here I have to exchange x and x prime. Yeah, this will be x minus x prime. But SGN s x minus x prime is minus SGN x prime minus x. It is clear. Therefore, t prime, we observe that our t prime with this constitutive law is just minus t. And therefore, with this constitutive law, t minus t prime is just 2 times t. Yeah. So now, if you insert, then you get let me copy this integral of b and the x. You write the final result. So this will be 2 times integral x minus delta x plus delta. Now I remember we got c u prime minus u of x prime minus u of x over x prime minus x, the x prime. Okay, And now we have the final result. Let us write down the first version of the equation of motion. Rho a u dot dot. This is the time derivatives, yeah? So this is 2 times x minus delta, x plus delta, c. So actually c can be a constant, but it can depend on x prime or x. Let us leave it inside the integral. If it is a constant, we may write it before. That means the root is homogeneous. X prime minus u of x prime minus x, dx prime, plus f of x. Okay, the first we consider, the equation of motion for the root in a peridynamic framework. So similar, if you work with psi inside the integral, then simply replace x prime by x plus psi. And then you get from minus delta to delta. C, here you get x prime is x plus psi minus u of x over the length of the bond. Instead of psi, x prime, you get psi, and here f of x. This is the same, but with the change of the integration variable. So now we have the peridynamic equation of motion for the root. Compare with CCM. In CCM, the left-hand side was the same, but in the right-hand side, you got EA, U, now let me skip primes, D2U over dx2, second derivative. This is compare with the same equation in the classical continuum mechanics. So EA was the tensile stiffness, okay? Now we have the peridynamic stiffness C, but we show later it can be related to the tensile stiffness of the root. And the same body force f of x, the same rate of change of momentum, the difference is here in this term. Okay? In classical continuum mechanics, the interactions between the points were local or contact. Therefore, we got these derivatives. Instead, in PD, the interactions are non-local or long-range forces. Therefore, instead of the derivatives, we have the integral. Okay? The equation in CCM is called partial differential equation. The equation in PD is called integral differential equation. Because in the left-hand side, we still have the derivative with respect to time. They are local. But with respect to x, we have no derivatives. Instead, we have the integral. Okay? Yeah, in mathematics, in the classical analysis, everybody knows how to solve this equation. Okay, this is a linear equation, and there are many methods available. Okay, linear partial differential equation. There is a special chapter in analysis. Remember, to solve it, you need the initial conditions, two initial conditions. You have to fix u at time for x at time 0 and u dot. These are they are called initial conditions. Okay, and two initial conditions and boundary conditions. How many? Two, yeah, because the second derivative. And two boundary conditions on the left of the rod and on the right of the rod. Without initial conditions and boundary conditions, you have only the general solution with many constants, with several constants. But to give the values for integration constants, you have to formulate initial conditions and boundary conditions. Okay, if we go to PD, the integral equation, unfortunately there is no theory or general procedure how to solve it, even in the case of statics. Okay? There are some analytical solutions derived in the last 5 years for this, and we are going to present you this. But as far as I know, there is no general theory like here for this type of equation. We have to develop it. So, but anyway, you can solve this equation numerically. So then a numerical method will be presented as well in this course. So fortunately for this rod, there are some analytical solutions. They can be derived. And if you develop a numerical code, you need to compare your result with something to verify or validate, yeah? Always. And to do this, you need another analytical solution. Some of them are available, fortunately. So, okay. Great. Okay. One question which is important is about the boundary conditions. The initial conditions, they are clear, they are the same. But how to formulate boundary conditions? Because we have a rod, the rod has a finite length, okay? If the rod would be infinite, then we have nothing to do. We have just to solve this equation. But usually we have a finite rod, and we have to say what is going on the left and on the right, okay? And of course, this is required to solve this integral equation too. And this is my next topic, boundary conditions, 2.6. But first of all, remember the classical continuum mechanics. The balance of momentum for a part of the rod. So we have some part of the rod, something like this. Oh, it could be a whole rod or a part of it. So some part of the rod, okay? And remember the rate of change of momentum for this part, we derived it. It was n at x2 minus n at x1 plus the body force. What is here important is this one. This is the internal force applied at x2 and at x1. And this is exactly the force acting from the environment on the rod through the cross section. Okay? This is n of x2, n of x1. Okay? And remember the balance of energy. We discussed it as well. For the part of the rod, the kinetic energy plus the stored energy, and assume that we have elasticity. Then we have the equality. Otherwise, we should work with the inequality, but let's write the equality for the sake of brevity. Important is this guy. So, and here this is plus P, the body force. Again, this guy is the power supplied to the rod, the mechanical power supplied to the rod through the cross sections. Okay? Okay? Great. Now, in the classical continuum mechanics, it is clear. If you take this one, for example, assume that you have the cross section for cross section x likes xc, okay? Like this one. What can you specify? From the balance of momentum, you see here that the force supplied is N, okay? So you should equate N to something. What can you specify? N of xc, yeah? So then you may specify the power. The power is N times the velocity of x2. N of xc times the velocity of xc. Okay? And of course, you may specify at xc the displacement or the velocity. The displacement and or in the dynamics, the velocity. In the statics, the displacement is enough. So, okay. Some coordinate, some boundary here. It may be 0 or L. So, some cross section. Now, remember some examples, elementary examples of boundary conditions. Assume that at xc, the boundary is fixed. Now let me take again the black color. It's not. The boundary is fixed. What is to be specified? This is very simple. U is 0. Yeah? U at xc is 0. Only one boundary condition is required at the boundary. That's all. Okay? But from this, it follows immediately in the classical CCM. The velocity is 0 because this point doesn't move. No velocity, no displacement. And the power from this follows that N V at xc is 0. The power is not supplied. And why? Because the velocity is 0. N is not 0, but the velocity is 0. Yeah? And in classical mechanics, these type of constraints are called ideal constraint. That means the power is not supplied. Okay. Another example is free boundary. This is not a constraint. Free boundary at xc. So here the displacement is not 0. The velocity is not 0. Okay? What is 0? N, yeah? The force on the right is not supplied. Therefore, N of xc is 0. no forces, free boundary. But again, from this follows that the power is not supplied. Physically it is clear, the free boundary, the power is not supplied. Why? Because the power in continuum mechanics is the force times the velocity. The force is zero, the velocity is not zero, but the power is zero. Okay? You may imagine many other examples. For example, one example, you may connect the rod with a spring, or you may apply the force at xc. What do you have to do in this case? This case, n of xc is f, yeah? And the power is not zero, because the force is acting, and if the velocity of that cross section is not zero, then the power is not zero. So, of course, we may imagine many other examples of boundary conditions. Despite boundary conditions, there are the so-called interaction conditions or transfer conditions. If you have two rods and connect them together, okay, then you have to do a similar stuff. Not the same, but a similar stuff. So there are some important properties to learn. Actually, in PD, this is not so trivial to apply the boundary condition, because everything is non-local. Okay. But what is important, we may again say we have the supplied force through the cross section, something like this, and we have the power supplied through the cross section. They are valid in thermodynamics too, but the formulations are different. Okay. And remember, they may have more notion of ideal constraint. We can do the same in peridynamics. We may define the constraint to be ideal if the power is not supplied. And from that, we get some properties. Okay, now let's look what is going on in PD. So in PD, we have the same rod, but now this is our rod or part of it. But now this rod is interacting with the environment, R. Remember, it was R. And let us define the part of the environment on the right side, say R on the right hand side and R on the left hand side of P. Okay? If you have, remember, in the balance of momentum in the right hand side, we have the force acting from the environment on the part of the rod, yeah? Now we can split it into LP and RP, yeah? And now again, say this is our cross section, for example, XC on the right, and should be R. Let us formulate the force RR. So this is in the environment on the right hand side. Now let us formulate compute the force. This is the force supplied at XC, okay? This is F from on the right side on P. Now, remember the definition. This is the integral over P and the integral over R on the right hand side. And this is our dual bond force density. Okay. Now, if we need a boundary condition for the force, then we need to take this guy and equate to something, okay, to 0, for example, if nothing is supplied. And you see that it's a little bit different because we have a double integral. It's not just a value at some point, okay? We have to integrate over the region. But fortunately, this n, we introduce a cutoff, okay? Therefore, we may simplify this integral. The integral of p r n x prime x dx prime dx. So instead of p, so this instead of the whole part of the rod, we have only a small region here. Let me take it in red with the size delta, okay? Because outside of delta, the force is 0. Okay. Now, instead of p, I write xc minus delta to xc, okay? This is my p again. So this is xc, this is xc, and this is delta. Instead of the whole part of p, I take only a small one with the size of delta. But now regarding the second integral, we should be careful, okay? The second integral is over x prime. The force is over x, okay? The second is over x prime. One feature is that the length x prime minus x should be less than delta. Outside is no interaction, okay? Or because our x prime is on the right, our x prime is on R, okay? So here is our x prime. Maybe let's do a big picture for this too. So again, we have this part of the rod. This is our xc. So this size is delta. Let's say this is p delta. And on the right, we have the environment, delta. This is the finite size as well. And let us consider one bond, say, this and that. We have to consider all the bonds crossing xc, okay? And this bond has two coordinates. One is inside p, this is x, and one is inside r, this is x prime. Okay? So our idea is, so in this bond we have some interaction force N, okay? And our idea is to sum up all the interaction forces inside P delta, R delta, such that the interaction is that we are inside the horizon, okay? Therefore, for the first integral, we took xi minus delta xc, sorry. But for the second, we should take into account that the length of the bond should be less than delta. And because x prime is on the right, it follows that x prime minus x, okay, or x prime should be less then x plus delta. Therefore, for the second integral, I take from xc, okay, from xc, x prime from xc, but the second limit is x plus delta, and x prime, x dx prime dx. Okay. In some cases, it is convenient to work with local coordinates. Okay? Let's do it. The local coordinates are, let me copy this picture. Copy this picture. So instead of x and x prime, let me introduce two other coordinates. So let me take the green color, something like this, the green color. So assume that we at xc is the 0 point. And now let me introduce two coordinates. One to the left, this will be xi. This is the coordinate of the bond in the left, or inside PD, P delta. And let me take another color. Oh, this one. This coordinate will be eta. Not n, eta. So now you may replace x is xc minus xi, and x prime is xc plus eta. Now our double integral, I copy this. We can replace the coordinates now. First, the integration limits here will be, so instead of dx prime, we have now d eta, yeah? Instead of dx, we have minus dxi. This can be inserted here. And now we have to change the integration limits. So eta, you see here x prime is xc plus eta. And x is xc minus xi, yeah? Dx prime d eta. First, let us integrate over dxi. Let's check. Okay, so this is first, we have the double integral, but let us start with, so here we have n, x prime is x plus eta, yeah, xc plus eta, xc minus xi. Now dx prime is d eta. Here we have minus dxi. First, let us integrate over dxi. Then we have to replace the integration limits. So for x is equal x psi minus delta, we have to compute psi, yeah? And psi is x plus xc. Then we have something wrong. Let's look. So x is x psi minus psi, but here is x is x psi minus delta, yeah? Then what would be the integration limits? Limit here, delta, yeah? Yeah? Is it correct? It should be delta. Physically, this will be the left point, yeah? Psi is delta. Okay? This is our first point. It should be delta. And the second should be 0, yeah? For psi. Now it seems to be okay. Okay, now let's do the same for eta. Eta starts here, so the first will be 0, because here it was xc, yeah? But the second one will be so now x psi plus delta, x prime is x plus delta, so xc plus delta is the same as x plus delta, so xc plus delta, x plus delta, but x is x psi minus xc. So that means, what do we got? No. Sorry. So x plus delta is xc x prime is x plus delta, but x prime is, on the other hand, x prime is xc plus eta. And from this follows that eta, this integration limit of eta, is delta minus psi. So now x prime is x plus delta. This is the old limit, but this is x psi plus eta, and x plus delta is this guy. Now I get for eta delta minus psi. This is my final result. Okay. So now let us write it. So F, the force supplied for R delta on P delta, can be computed as the following double integral. So, to skip this minus, I exchange the limits. I write from 0 to delta, okay? So it will be from 0 to delta. And here it will be from 0 to delta minus xi. And xc plus eta. Sorry, this is the second xc minus xi d eta d xi. So now we computed the force acting from the environment on PD through the cross-section XC. And some guys in PD call this force flux through XC. This double integral is important. First of all, we can use it to formulate boundary condition, okay, on XC. If we say the force flux through XC is equal to some force, then this is a type of boundary condition, okay? Second, in peridynamics, remember, in the classical continuum mechanics, we have the internal force and we have a stress. In peridynamics, there is no stress. No stress is in the constitutive equation. Instead of this, we are working with the force density. But we may compute always the force flux through the cross-section. And if you divide it by the cross-section area, then you get a similar quantity. Some guys say a peridynamic stress, okay? And you may compare the results of peridynamics with the results of the classical continuum mechanics. So, now this is this double integral. Okay, the same approach can be applied for the power. Why? Because remember, the power supplied, we introduced the power supplied to the rod through the cross-section. And the expression was defined before, last week. The power supplied, this is the absorbed power, and the power supplied, LS is this one. Yeah, from R to P. Now we take this double integral. In this integral, we have n and the sum of velocities of the right point and of the left point. Do the same, replace variables, integrate, and you get the power flux. Okay? And then the idea is to use these two quantities, force flux and power flux, to formulate boundary conditions. Okay, I propose to continue on Monday with this. And now we stop. Our last point was to derive, to show how to compute the flux. Let us remember, we assume the constitutive law with some interaction function. Then we derive the peridynamic equation of motion. This is the integral equation. And then we started to discuss the discussion about the fluxes through the cross-section. They're important to formulate boundary conditions. They are important, very important in the classical continuum mechanics, maybe not so important, but they are important in peridynamics. Therefore, we derived the force acting from the environment on P, and by By this way, we computed this so-called force flux through the cross-section XC. So, hello everybody. Today we are going to finish the lectures about rods, and now the point 2.6 is called peridynamic fluxes. So in the last lecture we introduced the flux of the force through the cross section, and this can be used to formulate boundary conditions, but it is not clear how this force flux influences the balance of momentum, or more in other words, how does it enter the peridynamic balance law. So consider as an example the balance of momentum. The rate of change of momentum for any part of the body is the resultant force acting from R on this part through the cross section of the rod plus the body force. So now remember, this body force, like the force of gravity, was the same in all theories, but this FRP is different. This type of balance equation is general, but depending on the type of force interactions, local or non-local, we may analyze this in the classical way and in PD. Remember, in the classical theory, you consider remove from the rod any part with coordinates x1 and x2. So here you have some body force, F and F of x. This is included in this guy. But we need now to analyze FRP. In CCM, RFRP. This is our part, and here is some environment removed from the part on the left and on the right. And to model the action, mechanical action of exerted by the environment of this part, remember we introduced the normal force N at x2 and the normal force N at x1. These forces in classical continuum mechanics are contact forces. So they are applied directly on the cross sections. And FRP is then N of x2 minus N of x1. This is CCM. So the force flux is defined by this way. Now, let's do the same in PD, or no, the same, but similar. Let us define FRP in PD again. Now, again, the picture of our rod, including the rod itself and the environment. So you have now this part of the rod with the coordinates x1 and x2, and now let R minus be the environment. This is our part. R minus be the environment on the left, while R plus will be the environment on the right. And so the resultant force acting from R on P will be splitted. Remember, the force is additive. That means the resultant force is the sum of forces. And now we can split R into R minus P and R into R plus P. the physical meaning, this is the action of R minus on the part P, while this guy on the right is the action of R plus on P. Now to introduce the fluxes, peridynamic fluxes, let us consider the following regions. Let us specify this region, which is going to infinity on the left, up to x now. Let this will be B, part of the body of x1 minus. x1 is this cross section, and bx1 minus is the whole region on the left. The part on the right, this is bx1 plus, and this part connects the part P of the rod and the environment R plus. Okay, now do the same with respect to x2. Let me use this color. If you take x2, then you should consider this region. This will be specified B x2 minus, and this is the connection of R minus and P, while this region is B x2 plus is the same as R plus. Now this can be written as follows. Let us take the first guy, F R minus P, and write the following thing. Instead of P, I include now P connected with R plus, but I should subtract the force supplied on R minus on R plus, because I added it here. Do the same with the second guy. This is F. The second guy will be F R plus R. But now, instead of P, I write R minus connected with P, and subtract F R plus R minus. So the first guy is nothing else. We can replace it by F. R minus is Bx1 minus, but P connected with R plus, you see here this red guy, this is Bx plus, Bx1 plus. So now let's take this guy. This is F Bx2 plus and Bx2 minus. And the last guys are minus F R minus R plus minus F of R plus R minus. So then remember the following thing. For any two regions we derived it at the beginning, the force acting on A on B is minus the force acting from B on A. That means F or FAB plus FBA is always 0. Therefore, this is exactly what we have here. We have sum. If you put minus, then you can write plus. So this guy is 0. Now we have the final result, which is very interesting. F RP is F Bx minus Bx1 plus 1 F Bx2 plus Bx2 minus. Okay, now to proceed, I do the following abbreviation. Let me consider F let me take this guy, and instead of x2 I write any x plus and any x minus. So what is the meaning of this? If I have a bar, it can be infinite, including the whole environment on the left and on the right. And I split it in two parts by the section x. Then I have bx minus and bx plus. And this f is simply nothing else than the action of bx plus on bx minus. Let me specify, abbreviated by NPD of x. This is my abbreviation. Now you may insert as x x2, then you get this guy, and you may insert as x x1, then you get not this guy but something different. But again we use this property, the action is minus reaction. And then we may, instead of this guy, we may write the following. We may write f r p, this is minus f, and now exchange the regions. We have bx1 plus bx1 minus plus f bx2 plus bx2 minus. Now this is exactly minus n of x1, but peridynamic n, and this is n peridynamic of x2. Now we have the final result. The action of the environment on P through all cross sections from the left and from the right can be represented as follows. This is again n, but the peridynamic n, x2, minus the peridynamic n at x1. So now you see here we got the same or similar equation like in CCM. The only difference is the definition of this n. In CCM it was the contact force, and in PD n is the force acting on Bx plus on Bx minus, or this is the same as the force flux through the cross section. Let us write it for any x, and PD of x is a double integral. Again we have to write here n, but instead of x prime x, let me write beta alpha d alpha, because my integration limits will be different. They will be from if you integrate over x prime is here. This is my beta. This is my bond. This is my alpha, and beta will be from x to infinity, and alpha will be from minus infinity to x. Now if we say that n, the interaction, and remember this is a dual force density, if we introduce the cut-off distance delta called the horizon, that means we have the interaction only inside the horizon, then this double integral can be written as follows: x minus delta. This is our lecture from the last the previous lecture, we analyzed this. Now we have here alpha plus delta and beta alpha d beta d alpha, or if you introduce the local coordinate system around x, then you may write from 0 to delta minus psi. This is n x plus eta x minus psi d eta d psi. Okay, now we have the clear meaning of the force flux. This enters the balance of momentum through this action of the environment on P at 2 points, and similar to classical continuum mechanics, this is a difference of two functions at x2 and x1. In contrast to classical continuum mechanics, these functions are force fluxes through the cross sections. Now, the similar stuff can be done for the balance of energy. There you have a similar flux of power flux through the cross sections. You may do the same. Why do we need this? Because, for example, to solve this equation, you may use this global form sometimes to formulate solutions, analytical or numerical. So the global, that means you formulate for part P the balance of momentum. There was another form called the local form, but here you may use this one. You may formulate analytical solutions or numerical solutions. This was used in classical continuum mechanics. And let's try to do it in peridynamics too. So in the second part, I demonstrate you how to apply this 2.7. We consider some only one elementary solution. There are many elementary solutions. Consider the root. Assume that the root is fixed on the left and it is homogeneous, and on the right you have this is our root of the length L. Let's say P as usual, L is, and here we have the environment, and here we have the environment, because the root is fixed and sorted into the wall or something like this. But you may think about the testing machine and the tensile test. In this case, this rod is inserted into the testing machine, and on the right the force is transferred from the testing machine into the rod. How the force transferred, it doesn't matter. We simply draw here this F, and this F is given, it can be measured. Let x be the coordinate, and let us use the equation, the balance of momentum, and the constitutive equation to solve this problem. First of all, assume we have no body force here, nothing like force of gravity, and we have statics or quasi-statics. That means this force is applied slowly and the bar is going to deform slowly. That means we can assume that the rate of change of momentum is zero, and the momentum is either conserved or the rate of change can be neglected. The only thing what we have in the previous equation to consider is this one. The resultant force action of the environment on P is zero. This is the statics. Okay, in the case of CCM, I do it slow because it is well known. If R of P, if you formulate it for the whole root, this is N of L minus N of 0, 0. That means N at L is N at 0. N at L is the boundary condition. This is your testing machine. It is acting on the rod at this cross section. And N at 0 is the reaction force from this clamped edge if you remove it. So they are the same. Furthermore, if you consider any part of the rod, say this P1, 2, for example, with the coordinates x1 and x2, and x2, you may formulate the balance of momentum as well. This is the statics R12 on P12, 0, the same. That means n of x2 minus n of x1 is 0. That means n of x2 is n of x1. That means does not depend on x. It is the same for any x. Therefore, n of x is constant. And so, applying the boundary conditions, condition 1, you get that n of x is f. This is the first part of the solution, and the second part is to apply the constitutive equation. In classical CCM, it was EA times the strain. This is the tensile stiffness. E is the Young's modulus. A is the cross-section area is F. That means EA du over dx. Remember the strain from the classical continuum mechanics is F. And now du over dx is F over EA. Integrate, you get u of x is fx of F over EA is x times x plus constant, and use the boundary condition on the left. From that follows that C is 0. Now this is the final solution of CCM. U of x is F, the applied force over EA over the tensile stiffness times the coordinate. And if you apply the tensile test, you measure the displacement at L. It means you get FL over EA. The force can be measured too. And by this test, if you know the displacement, you get the Young's modulus from the test. Results? Okay. Now, do the same in PD. In PD, remember, PD, our main result was that we have again FRP 0. And you may formulate this for the whole rod and for the part of the rod, and you get the same. The only difference is you have to write NPD, 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 NPD everywhere. Let's do it. So, first of all, NPD, this is the forced flux at L is equal to F. This is our PD boundary condition. Okay. NPD is the force flux through the cross section L. And the second result is NPD for any cross section is constant. And this constant is equal to F. So this is the first part of the solution. In the second part, we do the two following things. First, the peridynamic flux. I take this integral for n PD at x. And then remember, for n small, this is the bond force density. We should use the constitutive equation discussed before in our previous lectures. This is this one. Remember this discussion, and we use the constitutive equation for T, for example, this one. or that one, c u prime minus u over xi. Let's use this one. So n is t minus t prime, and t is c u prime minus u over absolute value of xi, and or x prime minus x, and then insert it here and take the integral. So let me write it here shortly. So n x prime x is t x prime x minus t x x prime, and this is c u prime minus u over absolute value x prime minus x, and this is c u minus u prime, because I should exchange the variables, but this is 2 times c u prime minus u x prime minus x. Now insert it into the double integral. So NPD of x, this will be, let me open this integral 0 delta minus xi. Now you have u x plus eta minus u x plus minus xi divided by xi plus eta. You don't need to write the absolute value because they are positive, 2c, and that's all. The eta dxi is f. So the next step is to solve this integral equation. The following thing is here visible. You see here inside the integral we have a function of x. If you integrate it over xi eta, you get some function of x. But this function at the end should be constant. Okay, therefore we are looking first for the condition at which this function does not depend on x. There is some constant. It can be a function of nu xi and nu, but not of x. So, and if you analyze it, there are several approaches to analyze it. For example, you may expand it into the Taylor series around x, these two, and then insert and analyze under which conditions it is possible. And if the function u is smooth, then you find out that the condition is du over dx is some constant, or u of x is some a plus b times x. That means this condition can only be satisfied if the function u is a linear one. There is another way to prove it. For example, take the derivative of the left-hand side over x, and the same on the right-hand side is 0. And after some analysis, you get this again. Let me skip this proof. So this the function u can only be linear. This is our result. And from u 0, 0, again, we get u of x is some constant b times x. So now remember we discussed the Born strain. Verify at home that the constant b is exactly the Born strain in this equation. Insert it and compute the Born strain. You get b. Now the final step is to compute this double integral. So u of x is now epsilon b times x. U of x plus eta is epsilon b x plus eta, ux minus xi is epsilon b x minus xi, and then insert ux plus eta minus ux minus xi over xi plus eta. This will be epsilon b x minus x will be 0. This will be simply epsilon b. Okay, insert into the double integral and you get NPD. Now we write all constants before to c epsilon b, and here inside the integral we have nothing, just the constant. So we have from 0 to delta, delta from 0 to delta minus xi, d eta dxi. Okay, d eta dxi. Now integrate it. This will be 2c epsilon b, integral from 0 to delta. If you integrate this, you get eta, and if you insert the integration limits, you get delta minus xi dxi. Now take the second integral. This will be 2c epsilon b delta xi minus xi power 2 over 2 from 0 to delta. Insert, it will be delta power 2 minus delta power 2 over 2. This will be delta power 2 over 2, and the final result will be c epsilon b. Great. Now, this is the solution of PD. Nothing new. We got that the peridynamic flux is the linear function of the bond strain, but the assumption was that the rod is uniform, homogeneous, everything same, and therefore we got the same result. See that epsilon b is b, or this is du over dx. They're similar, or the same as in the classical theory. Therefore, for the uniform strain state, the bond strain in PD is the same as the strain in the classical theory. And therefore, we may now we may use this equation or this one and say the results are the same and should be the same. And we may identify the constant C. So if we perform the tensile test, then C epsilon b is F. But this, sorry, we forgotten delta quadrat. But this, if you apply the tensile load, measure the elongation, then you get the Young's modulus and the cross-section area. So here you have the tensile stiffness. And now you can identify the peridynamic stiffness. C delta quadrat is E times A from the tensile test. That means C is EA over delta quadrat, delta power 2, sorry, delta power 2. And now by this way, first we solved the problem. Second, we identified the one parameter in the peridynamic theory. This is the stiffness. And now you may go back and remember we derived the local form of the balance of momentum or the equation of motion in PD. Now you may insert this constant C. Where is it? Here is it. So you may take this one or that one. Let's take this one, and C is now EA over delta power 2. Let us copy this equation, because later on it will be solved for different cases of boundary conditions and loadings. And now we completely derived the 1D peridynamic equation. So now you have, sorry, this is the wrong place. This is the wrong place. We have to go to the end, and we add this here. This is our final result. Now I replace C by 2 times EA. If the rotor is homogeneous, then everything is constant over delta power 2. This is now the final equation of motion for homogeneous rotor in the peridynamic framework. So, okay, thank you for your attention.